So we had this circuit. And already I have defined the events carefully. These were the relays. I explained what relays are, and probability of AI that the relay is closed, probability that ith relay is closed is given to be small p, and probability that the ith relay is open is given to be 1 minus p, where I is equal to 1, 2, 3, 4. That was the part, that was the thing that I actually wrote until my next previous session ended. Now here, in this particular problem, you are going to see that how to deal with the kind of scenario I'm dealing with and how mathematicians or statisticians develop theories. Now, carefully observe here in this particular scenario, several cases that you have to consider. You have to consider the cases, those cases where the relays will be closed, but there will be a circuit, because I'm interested in that. So I am considering case 1. Now you see that if I close the relay 1 and keep other relays 2, 3, 4 open, then there will be a circuit from L to R, not along this path where relay 1 and 2 are in series, but along this path, but along the path where 3 and 4 are in series. So I can keep one closed and rest of the relays can remain open. Okay, so this is one case where there will be kind of circuit along a path from L to R. This is one event. I'm just marking the events. Another case you can consider is that you can do the similar thing with A2. Then also there will be kind of circuit from L to R. Then you can do a similar thing with A3, keep it closed and rest of the things is open. That is another. And the last one, you can do the same with A4, keep the A1, A2, A3, 1, 2, 3 open, closed, and A4, I mean the relay 4 is open. So this is the case. These are the cases, 4 cases, 4 sub cases under case 1. Now I'm interested in finding what is the probability of the events in this particular case. Okay, so if this is the case, probability of A1 bar, A2, A3, A4, this I want to calculate. Probability of A1, A2 bar, A3, A4, I want to calculate. Here I want to calculate probability of A1, A2, A3 bar, A4. And lastly, here I am going to calculate probability of A1, A2, A3, and A4 bar. But here at this moment, we are stuck with a problem. Mathematicians stuck with a problem that they know that when A and B are independent, this is a known result, that probability of A intersection B is equal to probability of A into probability of B. But the question is, does it happen? The question is, does it happen? Does it happen? By does it happen, I mean whether the same scenario happen for events like A and the complementary event of another event, B bar. So can I say that if A and B are independent, does it imply that A and B bar is also independent? If it is so, then I can write this probability as the product of individual probability. If this result is true, then I can write it as probability of A1 bar, probability of A2, probability of A3, probability of A4. If my result, my claim is true, I can write it as probability of A1 into probability of A2 bar, probability of A3 bar, A3, and probability of A4. And here I am writing probability of A1 into probability of A2 into probability of A3 bar into probability of A4. And if it is true, I can write here probability of A1 into probability of A2 into probability of A3 into probability of A4 bar. If this result that I have written over here, star, if it is true, currently, you remember that it is yes, the answer is yes, this result is true. But let me finish the problem first. This is a very valid result. If capital A and capital B are independent, capital A and capital B bar is also independent. It's a very valid result. I'm going to discuss after the problem is done. So right now, right at this moment, you remember that it happens. Yeah, yes, it is true. I'm eligible to write the things in the following manner. And if it is so, then you see by the given probabilities, each of the probability can be expressed in the following manner. So I can write it as 1 minus p into p cube. This is 1 minus p into p cube. This is 1 minus p into p cube. And this is 1 minus p into p cube. Okay, but here in this case one, if you carefully observe that these individual events A1, A2, A3, A4, they are independent. Okay, but if I collectively look at the events A1 bar, A2, A3, A4, if I collectively look at the event this, if I collectively look at this event this, if I collectively look at this event, these collective events, they are not independent. These are mutually exclusive. So if this is happening, if this is happening, the other rest of the thing will not happen. So we have actually got this. We have actually got this. Remember one thing, A intersection B, here in this probability theory, we always not write intersection just to save our time. This is often written as A into AB. It is not A into B because A is an event, B is an event. You cannot multiply two events. There is no meaning in this. So A intersection B will be abbreviated as AB. That's why I have written it in this manner. In between the events, there are intersection symbols. Okay. But remember, these collective events, they are actually mutually exclusive. All these events are mutually exclusive. So I'm writing, I'm actually interested in the union of these events. So I'm interested in union of these events. And you also, you know from our previous class that when A and B are mutually exclusive or disjoint, then probability of A union B is equal to probability of A plus probability of B. Okay, so if it is so, then my probability becomes, my probability now becomes, in this particular case, it becomes probability of this quantity, probability of this quantity plus probability of this quantity plus probability of this quantity. So actually we are getting 1 minus p into p cube plus 1 minus p into p cube plus 1 minus p into p cube plus 1 minus p into p cube. And how many things, this kind of things are there? 4 into p cube into 1 minus p. This is my number one. This is my probability for case one. The problem is not yet done. Let us go to the, you just quickly take the screenshot of this particular problem and let's move on to the. Okay, TK. Chat box in someone has written that others are facing trouble, so that's why they are not able to enter. Anyways, so this is the probability which is for case one. Now, this is not the only case. This is not the only case, and therefore, let us talk about the other cases that may happen here. Now, case number two. Case number two, I am considering that, just look at the relay. I'm drawing the relay once again so that it remains in front of you. This is the relay. This is the structure of the relay. Okay, this is your L, this is your R, this is 1, this is 2, this is 3, and this is 4. Another case may happen that the relays 1 and 2, they are closed, but relay 3 and relay 4, they are open. This is one case that can happen. Relay 1 and relay 2 are open, and relay 3 and relay 4, they are closed. This is another scenario that can happen in which you are going to get a kind of circuit from L to R. So under this scenario, if I want to find the probability of this quantity, this event, then by the similar multiplication theorem, we can multiply the probability of these events. We can multiply the probability of these events. And if I substitute the values, you are going to get probability of A1 into probability of A2 plus into probability of A3 bar into probability of A4 bar. So for probability of A1 into probability of A2, we get P squared. And for probability of A3 bar into probability of A4 bar, we are going to get 1 minus P whole square. Similarly, here also we are going to get probability 1 minus P whole square. And again, as the case that I discussed in the previous scenario, these collective events, that means this event and this event, these collective events are actually mutually exclusive. So the respective probability that either this event or this event happens, since these collective events are mutually exclusive, so their probability is sum of their individual probabilities. So because probability of A union B for mutually exclusive event is PA plus PB. And if I do so, I have to add the probability this and the probability of that. So we are going to write it as P square into 1 minus P whole square plus P square into 1 minus P whole square. And this implies 2P square into 1 minus P whole square. This is your number 2. Is there any other case where the particular circuit will happen between, where the particular circuit will, what did you write? 2P square? Yeah, right. Yeah, all right. Is there any other case where the particular circuit, there will be a kind of circuit from L to R? Case number 3, where you can consider that all the relays A1, A2, A3, A4, all the relays, they are closed. If all the relays are closed, then there will be a kind of circuit from L to R. So if I am interested in finding the probability of this quantity, then it will be the probability of these events are independent. So we are going to multiply the probabilities one by one. So let me write just for your sake of understanding, because sometimes you may become confused what is happening. So this will become P to the power 4. If you observe it, if you observe now carefully, I do not have any other cases. I do not have any other cases apart from this. I don't think so any other cases are there. So case 1, case 2, case 3 are the only cases, and we have got 3 different types of probabilities. Therefore, the total probability will be, try to add them up. So we get P to the power 4 plus 4 into, what was that? 4P cube, 1 minus how much? 1 minus P. Okay. 1 minus P into P cube plus 2P square into 1 minus P whole square. Now you can simplify this quantity. Let us simplify. You also simplify and try to find the probability. So we get 4P cube minus 4P to the power 4 plus 2P square into 1 plus P square minus 2P. And then this implies P to the power 4, 4P cube minus 4P to the power 4 and plus 2P square plus 2P to the power 4 minus 4P cube. This will cancel one another. and this will become p to the power 4 minus, minus 4p to the power 4 plus 2p to the power 4, that is minus 2p to the power 4 plus 2p square, and this becomes minus p to the power 4 plus 2p square, and if I take p square common, this will be 2 minus p square. So this is the answer to our given question. Now, solving question in statistics, solving question is not only important, understanding the thing is very important. Many intricacies, if you give a deep thought to the problem that I have described over here, you will, I don't know whether you have actually observed it or not. Just take a screenshot of this page. I'm going back to the previous page. Just quickly take the screenshot of this page. Okay, and now I'm going back to the previous page. If you carefully observe in the question, okay, it is say you see that the given probabilities are small p and 1 minus p, and you know that small p is a number which lies between 0 and 1. Similarly, 1 minus p is also a kind of number which lies between 0 and 1, but they are not interested in the values. They could have given me half or half, p to be half or 2/3 or whatever, but they are not interested in values because this is a very general problem. Remember, probabilities are not actually calculated. Probabilities are, as I told in previous class, the probabilities are imposed on the system, considering the system to be unbiased, but they are not considering the given system to be unbiased. We do not know whether the given circuit is unbiased. We do not know whether the given circuit is unbiased. It is not actually, whether it is actually, free of any disturbances, physical disturbances. We do not know this. Once they claim that p equals to half, if they write that each of the probabilities having closed is half, if they do so, since there are 4 events, if they write 1/4, not half, because there are 4 events, so that total probability is 1, then immediately they are actually assuming that the circuit is unbiased. Who told you that the circuit is unbiased? We may be dealing with a very biased system, so they have not mentioned the values of the probabilities. But by this calculation, we have understood how to find the probabilities in this type of scenario. One can complicate the scenario in the following manner also. Okay, consider this type of thing. And you can complicate the situation, and you can try to find out under what conditions the particular event will be, a particular circuit will form between two terminals. Before I stop discussing my today's session, one fundamental question that needs to be answered. The fundamental question is, during the entire calculation, we have assumed that this can be written. Okay. However, we know that if A and B are independent, probability of A intersection B is probability of A into probability of B. But nobody has told us that whether, if we consider A and complementary event of B, whether we can write it as probability of A into, we can write probability of A intersection B bar as probability of A into probability of B bar. That claim which we have considered to be correct, let's just see whether it is indeed correct or not. Okay, otherwise my discussion will remain incomplete. So I am going to check whether the thing is correct or not. So the result is, if capital A, they are claiming that if capital A and B are independent, then A and B bar are also independent, Okay. So how can we prove it? We can very easily use the axiomatic approach. Capital A and capital B be two events. And from our previous session, you know that probability of what we want to check? If I want to check that A and B bar are independent, actually we need to show that probability of A intersection B bar is equal to probability of A into probability of B bar. This is our objective. Okay, now what we can do, we can start with the left hand side. So we can write probability of A intersection B bar. And we know from our previous theorem that I discussed in the previous class, if you cannot remember, you can go to my YouTube video and you can see that this has a formula. A intersection B bar means A is happening and B bar is not happening. So this portion, okay, so this can be written as probability of A minus probability of A intersection B. This is a theorem that I proved in my last class. But as we see that A and B are independent, so probability of A intersection B is equal to probability of A into probability of B. We can substitute the given result over here. So we can write it as probability of A minus probability of A into probability of B. And if I take probability of A common, we get 1 minus probability of B. And that is nothing but equals to probability of B bar. Just see, we have got our right hand side. We have got our right hand side. So yeah, indeed it is true that if A and B bar are independent, and then if A and B are independent, A and B bar are also independent. Not only this, if you consider probability of A bar intersection B, then also we are going to get the same scenario. A bar intersection B means A is not happening, but B is happening. This quantity, this side, this is your A bar intersection B. Okay, so we can write it as probability of B minus probability of A intersection B. And by the similar argument, we can write probability of A intersection B to be probability of A into probability of B. And which is, if you take probability of B common, we are going to get 1 minus probability of A, which is probability of B into probability of A bar. So you see, A bar and B are also independent. If A and B are independent. Okay, and before I conclude my session, last result that I need to talk about is very important. If A and B are independent, then not only A bar and B, or A and B bar, complementary event A bar and complementary event B bar are also independent. This is quite different from the earlier proof. You may face difficulties, so I'm going to help you in this regard, how to show this. These are also independent. This is my last topic of today's class. So we need to show that probability of A bar intersection B bar is equal to probability of A bar into probability of B bar. Okay, this is our requirement. We need to show this. Let's start with the left hand side. Probability of A bar intersection B bar. Now try to recall De Morgan's law. De Morgan's law says that A bar intersection B bar is equal to A union B bar. A bar union B bar says that A intersection B whole bar. So we can apply this result over here. In place of A bar intersection B bar, we can write A union B whole bar. Now, since A and is an event, B is an event, so A union B is an event, and therefore A union B complement is also an event. So we can apply the formula probability of A bar equal to 1 minus PA. We can apply this formula over here. So we are writing it as probability of 1 minus probability of A union B. And one result that I left with you to solve, you are actually supposed to solve this result. I don't know whether you have done it. This useful result will be applied over here. So we will try to implement this result in this case. Okay, and now you just little bit of mathematics. So 1 minus PA minus PB plus P of A intersection B. But remember that P of A intersection B is a kind of is A and B are independent. So probability of A intersection B is PA into PB. So I can rewrite the thing as 1 minus PA minus PB plus PA into PB. Now you factorize the thing. Now factorize. One quantity is 1 minus PA, and you take by minus PB common, you get 1 minus PA, and this gives you 1 minus PA, 1 minus PB, and which is PA bar into PB bar, which proves our given result. So these three fundamental axioms are actually very important. You see in the circuit problem, actually we needed these results. Otherwise, if the result was not there, the circuit problems couldn't have been there. So do not think that statisticians or mathematicians always try to develop the result by themselves. They face a physical situation. They are unable to deal the physical situation, and according to the requirement, what they do, they try to develop mathematics so that they can proceed. Okay, so here is what I wanted to discuss with all of you in today's class. Tomorrow probably I have a class with you at 11:10, if I'm not wrong, single period class. Okay, so I'm stopping the recording.